好，
到时候我传给你，您确认一下。
好，好，这样可以了。那我们就请利亚可以开始。利亚 you can start your presentation now.
Okay, thank you so much. Okay, first of all, good afternoon, everyone. The Honorable Dr. Ke as my supervisor, and also the Honorable Dr. Chen and Dr. Ma as the jury. Thank you so much for attending my thesis oral defense, and then thank you so much for taking the time to be able to assess my oral defense presentations. First of all, I would like to introduce myself. My name is Lia Asuti, and then currently this year I'm become the second years of master program of information technology and application students in National Quemoy University. In this opportunity, I would like to present my thesis oral defense as one of the requirements for getting my Master of Science degree, which has the title Optimizing Contention Window in IEEE X02.11 Wireless Networks Using Deep Reinforcement Learning to Enhance Network Performance. Okay, so the first one I would like to talk about the outline to make my research presentation systematically. The first one of the first chapter, I would like to talk about the introduction. Second one, I would like to talk about the literature review or the related works. The third one, I would like to talk about the proposed algorithm. The fourth one, I would like to talk about the research result and analysis. And then the fifth one, I would like to talk about the conclusion and the future works. Now, move on to the first chapter, which is introduction. The number of internet users is increasing as time goes on, especially in these current years. We know when the COVID-19 cases is arising. For example, at the education sector, all of the teaching learning process is moving to the video conference, such as Google Meet, Zoom meeting, or etc. And then one of the way to make the devices such as laptop, computer, or even handphone can connect it to the internet is using connected to the wireless networks. So the popularity of the using wireless networks will result in the throughput degradation when a loss of nodes or stations are transmitting the data packets. While when the data continuously growing, sending and receiving data simultaneously will lead to the increasing of the collision rate, especially in the heavy network loads. So it means it will have the throughput degradation for the wireless network itself. As a basic access mechanism to prevent the collision rate, by starting from the initial transmission, it is corresponding to the carrier sense multiple access with collision avoidance, or CSMACA method that relies by binary exponential backoff or BEB algorithm. So for your information that the binary exponential backoff BEB algorithm itself is the traditional or classic of CSMACA method. And then when the channel is detected as being idle before transferring the data packet, the nodes or the station itself will wait for several indefinite period of time. And then the waiting time itself, it is corresponding to the contention window. So the contention window, or the abbreviation is CW, optimization has significant impact on the network performance. So that's why there is dozens of the research paper that want to optimize the contention window to achieve their own objectivity. Now, in this slide, I would like to talk about why selecting the appropriate contention window size is very important as a collision avoidance techniques. So here is the theory. If the value of contention window is small, the stations just need to wait less time for data transmission, and then it has the disadvantage, which is the stations have a higher probability to select the same contention window value, which will easily cause collisions. Furthermore, if the value selected by the contention window is large, It is not easy for the stations to select the same contention window value. Therefore, it will not cause collision, but the stations need to wait for a long time to send out the packet. So in here, I would like to talk about the research motivation that motivated this research paper. So the first one is presented by the Wittmanski and Schott that proposing the centralized contention window optimization with deep reinforcement learning by using deep Q learning network, or we can say that is CCOD DQN algorithm. Here, the upright is the topology for CCOD DQN, which is stations transmit data to the access point, or the AP. We can see here that the authors, they are defining the agent that located into the access point, and then the agent itself will observe the state and take the action to choose the appropriate contention window values. However, the disadvantage of this proposed method of the CCOD DQN, they are mainly consider the state rather than adjusting the contention window value, whether that is failure or successful for the packet transmission. In addition, we have the Ko et al. That proposing the smart exponential threshold linear, or SETL algorithm, that took the advantage of the EIED, or exponential increase, exponential decrease, and also LILD, or linear increase and linear decrease. We can see at down right here, which is the figure of the contention window size schemes of SETL algorithm. We can see here, Ko et al. Define the contention window threshold value that equal to 512. And then we have the figure which contention window size versus back of stage. And then when the contention window size is lower than the contention window threshold value, the contention window size value is adjusting exponentially. And then when the contention window size is bigger rather than the contention window threshold value, the contention window size is adjusting linearly. So in this research paper, we'll present the new approach to the contention window control mechanism by applying the deep reinforcement learning agent, or specifically DQN principle, to adjust the contention window threshold value, whether it is exponentially or linearly. Now, I would like to present about the research contribution of this paper. The first one is the SETL DQN, or Smart Exponential Threshold Linear with Deep Q-Learning Network algorithm, will be proposed to optimize the contention window threshold on the smaller and the bigger contending stations in order to avoid waiting time before the station sending out the packet data. And then the second one is reducing the collision rate will be defined at the smaller and bigger region of the network loads. And then the third one is maximizing the normalized saturation threshold will be determined by the SETL DQN algorithm in the static and dynamic user scenarios. Now, the question is, what is the saturation and what is the static, and also what is the dynamic? Now, I would like to explain what is the saturation first. Normalized saturation threshold. Saturation means that we will assume that the stations always has packet to transmit, which equal or the explanation for the saturation mode. And then, what is the static itself? Static user scenarios, which mean there's in the several definite of time, it will have the fixed number of stations were connected to the access point. And then, what is the dynamic user scenarios? It means that in the first several period of time, it will have removing or adding the stations that were connected to the access point. Now, we will continue to the explanation of the literature review or the related works. We can see here, the first one I would like to talk about the IEEE X02.11 WLAN, or the Wireless Local Area Network, CSMACA, MAC protocol, or Medium Access Control Protocol. The stations transmitted the data, which will be detected by the CSMA method and checking the channel status to know the presence of the data packet of each station. So we know that in this recent decades that a lot of the research paper that have the integrated research, which means that will combine between two big scope. And then in here, in my research paper, I would like to combine, which means that from the AI to the WLAN, which means I would like to implement the reinforcement learning as one of the field of the machine learning, such as, and we know that the machine learning have the three fields, which is supervised learning, unsupervised learning, and then reinforcement learning. And then the specialty for the reinforcement, why I chose this reinforcement learning, because it is special. Why? Because it is using the trial and error method. And then one of the classic of the reinforcement learning method, which is skill learning, that has several parameters. It has the agent that took the action to the environment, and then the environment itself will give the reward to the agent. And then what is the state? The state is represent the current of the environment. Now that in the one of the field of the reinforcement learning itself, it has the deep reinforcement learning that have that adopt the deep neural network or deep learning. Now we can see the differentiation between the topology of Q-learning or reinforcement learning and deep reinforcement learning. We have the agent in the current state that before taking the action, they have the policy. What is the policy itself means? The policy means that the strategy before the agent took the action to the environment. And then for the deep reinforcement learning, there are several of the algorithms such as DDPG or deep deterministic reinforcement learning, and also we have also deep Q-learning network. So we can see here that DQN is the extension of the classic reinforcement learning, which is Q-learning, that instead of using Q-table, the DQL techniques use the deep Q network or DQN. The network is from DNN, same like deep reinforcement learning, to calculate the approximation value of Q function and in the state and took the action. And then here we are using the tools and for the environment, which is POMDP, partially observable Markov decision process, which is representation of the agent decision process. Actually, there are several of the agent for the agent decision process techniques, but I will use the POMDP to make the performance have a better performance. And then here we have the tuple for the POMDP, which is state, action, omega, or the observation, and also have the transition, and also we have the observation probabilities, and we have the reward that represent a 6 of POMDP elements. And then, so that's why just now I say that there's a lot of the research have the integrated research, and we have the using of Q-learning and DQN for contention window optimization. So many research work for proposed for algorithm by adopting Q-learning, DQN in wireless network environment to enhance performance and optimize contention window parameters. Now, I
would like to interrupt you for
okay.
I have a question. Please go back to the last slide. Yeah,
Okay.
in this slide, the two figures in the middle one, there is a dash line. You see, the dash line. Dash line. Yeah. Why there is the dash line, and in the other figure, the right one, there is no dash line. What's the difference?
Okay, what is the difference? The difference is all because the environment will moving. What does that means? If we are talking about the agent will just take the action to the environment, whether in the current, previous, or the next environment. Which means if in the current environment, it will give the agent the current reward. If moving to the next environment, it will give the agent the next reward and also the next state. So
the next state, the next reward.
Yeah, the next reward. Yes, that one.
But why the right one there, it did not show the next the next stage, the next reward, next action. Why?
Okay, why? It is all because the agent will take the action, and then it will have when the agent will take the action in the current environment, it will have the related with the action before the action, the previous action. Yes, but when here in the environment, they give the reward and give the state, it has no any correlation with the previous reward and the previous state.
You means that the
So
previous state is independent with the current, the new state.
yes, it's all independent, but the decision process for the action, it always has correlated each other. Yeah, I think later I will explain there is a correlation with the discount factor.
Oh, okay.
That one.
Okay. We go on.
Okay, thank you. So thank you, Professor,
you.
for your question. Okay, and then now I would like to explain about this research paper proposed method, which is SETL-DQN. So, but before I talk about the SETL-DQN for this research paper algorithm, now I would like to talk about the binary exponential backoff or BEB algorithm as the classic or the traditional CSM-ACA method. So in here, we can see that the minimum of the contention window or initial contention window is equal to 16, and then the maximum of the contention window is equal to 1024. So as the information that I'm using the X0 2.11 AC as the experiment environment, and then here for the contention window minimum to initial contention window to the first contention window, that is multiplied by 2 until the maximum contention window. So it means when the collision for the BEB algorithms, the contention window will just multiply by 2, and then in the adjustment of the action value is integer between 0 until 6, which means the range of the contention window value for BEB algorithm is from 16 to 1024. So in this BEB algorithm, it will become the comparison between SETL-DQN, CCOD-DQN, and SETL, and also BEB algorithm or standard X0 2.11 AC. And then for a standard X0 2.11 AC and CCOD-DQN will adopt this scheme for the collisions for these schemes. And then the next one is I would like to talk about the smart exponential threshold linear or SETL algorithm. Here we can see. Actually, I already explained at the first introduction. So we can see here that we define SETL algorithm defined contention window threshold value, which equal to 512. So when the contention window is lower rather than the contention window threshold value, it will multiply by 2, which means that moving exponentially. But when it's bigger than the contention window threshold value, it will add by the 32, which means that adjusting linearly. So here, and here, the SETL-DQN, this research proposed method will adopt the SETL algorithm. Now, I would like to move forward for the proposed SETL algorithm that use the partially observable Markov decision process for POMDP. Now, in this SETL-DQN algorithm, we define the agent. The agent is located in the access point, and then the state, and it has the set that the current situation of the exact status for all devices that are connected to the wireless networks. And then we have the transition probabilities, T, and after that, the transition between the current state and then the next state. And we have the observation. the collision probability which corresponded by the current collision probability, or we can say PCO. And then the next one is, here is the point, which is for the acetyl DQN algorithm actions. The range of the new contention window threshold value is from 128 to 1024, which have the adjustment of the action value is an integer between 0 to 7. That means that the contention window threshold is equal to 2 until 2 square root of 7 multiplied by 1 plus action. And also, we have the history of recently observed collision probabilities, or we can say there is a symbol is HPCO. That means that previous state and then the current state. So what is the differences between the previous state and then the current state? So if we compare between the previous state and then the current state, then we will know that it will explain the topology before, and that the reinforcement before. The previous state and then the current state, they will for example, and when the agent take the action at the current state, it will see the previous action. What it means that the previous action means that we have a bad and also good. Good means when the collision rate and the collision probability is dropped, it means good actions. And then if the collision rate in the previous state is increased, it means it's bad. So in this current state means that when the previous state performance is good, it will applicable for the current state. If the previous state actions is bad, which means the collision rate is increased, it means that in this current state, it will not applicable, and it will update and make a different strategy. So the difference is why I'm using the DQN, and then before it's using the reinforcement learning. I'm using the history of recently observed collision probabilities, which mean have the correlation between the current state and the previous state, because reinforcement learning is using the trial and error, right? And then here the HPCO will good for the performance, but in the reinforcement learning, they are independently. The current state will just have the current state, and they are independent. But in here, it has the correlation. That one. And then the next one means that this algorithm, acetyl DQ algorithm, will evaluate the agent action based on the collision rate. Okay. And then the next one is the reward. So I'm using in this acetyl algorithm, we have the reward, which is the network normalized throughput that is between 0 until 1, and then the network normalized throughput itself is the number successful delivered bits per second, and the obtained throughput is divided into the channel bit rate. So later I will show the experiments, the screenshot for the experiments. It will has the differentiation, which means that it will shows the aggregate throughput. And then here, the aggregate throughput means that it haven't changed into the normalized throughput. But in the graph, I will show the throughput that has been changed to the network normalized throughput, okay? And then the next one is discount coefficient, or gamma. So discount coefficient itself, if the gamma is close to 1, the agent will determine the importance of the future rewards. And then conversely, if gamma is close to 0, the agent will be worthless in the future rewards. So in here, that in the DQN, it's almost the same with the history of recently observed collision probabilities. They have the correlation between the previous state and then the current state. And then here, also, the discount coefficient, the gamma, the agent will determine the importance of the future reward. So they will just update the new strategy to get a better result. And the simple one of the explanation is that one. And also now I'd like to explain about the proposed SETL DQN algorithm method. So like what I said before, that this research paper will adopt the principle of the DQN to the SETL algorithm that will determine the contention window threshold value via exploration under the various network scenarios. And then here, I will show the code of SETL DQN algorithm. And we have the HP call, which means the history of recently observed collision probabilities. And then the load itself is data since the last interaction. And we have the action, previous action, state, reward, and then also the new contention window threshold value. So actually, the SETL DQN is divided in the learning procedure and also evaluation procedure. So it has the correlation between the exploration and exploitation. Now, I would like to talk about the procedure for the learning process. So in here, in the beginning of the running of the SETL DQN algorithm, the contention window threshold is setting to 128. Then during the training period, the agent will generate different action value through the exploration by observing the collision probabilities, because we have the history of PICO. And after that, it will adjust the contention window threshold value. Now, after the training process gradually converge, which means that the degree of the exploration is decreased, it will move to the process for the exploitation, means it will move to the evaluation process. So we can see here that the contention window threshold value have then generated, and then it's sent to the neural network. That one. And then now I'd like to move to the research result and analysis.
Sorry, Leah, would you
Okay.
please go back to the next slide?
Mhm.
Sorry for interruption. In the pseudocode, the 9.4, what do you mean by step? What's the function of step? 9.4, agent dot step. No, that means the first line. Agent dot step.
Agent.
That's
Okay.
what
Okay.
step?
Okay. Agent that step means that the training neural network. So in the in the DQN, we have the experience replay pool. So the experience replay pool, it will record the state, action, and then the reward from, because it will have the episodes, right? Epoch. I mean, seems like it will training again at the first epoch, at the first first episode, second episode, and etc. And then in this agent step, the agent itself will save the experience replay pool that consisting of the state, action, and the reward as the training neural network. That one.
So step is another procedure.
No, the step is not another procedure. That is the process.
It's a process.
I mean,
so where to define the process in? Where do you define the process?
I mean, the step itself is the. What's that? I mean, because in this step, in the state, action, and then the reward, they are including the experience replay pool that the agent is take the action and etc. And then the agent will how to explain? Yeah, the step is the for a training this one. I think. Okay, can you repeat again the question?
Okay.
Sorry, I can. I think I will try to help explain. For this means during the training process, we need to we need to save the state, action, reward. We can save this data into a history memory. Then when doing the agent step means to chaining, to update the parameters.
That's what I mean. Yeah.
So what about another function, agent.act?
That is the action at the current state. Plus noise. Noise means at the it's the noise that for the training of the action, current action.
Okay.
Yeah.
Thank you. Please go on.
Yeah, thank you so much. Okay, the next one is I would like to talk about the research result and analysis. Okay, so here is the simulation result at the simulation setup. The SETL DQN algorithm that using the PAR and pedal provided by Baidu, and also the simulation environments was tested in the Linux operation system, and also we have the IEEE X02.11ac settings set simulation experiments parameters. So in here is the parameters of X02.11ac. We have the MPDU size that equal to 3,895 bytes. And also we have the physical header. We have the acknowledgement, and we have the X02.11 bit rate. We have the contention window minimum, which is CW0, which equal to 16. And also we have the CW maximum, which is maximum of the contention window, which equal to 1024. We have the slot time that equal to 9 microseconds. And we have the SIFS, which means the short interframe space, that equal to 16 microseconds. And also we have the DIFS, that DCF or distributed coordination function interframe space, that equal to 34 microseconds. So in here, we have the DQN parameters. So in here we have the parameters and also the value. Now we have the memory size. That the memory size itself is using for the experience replay pool that just now that we talked about this one, the agent step for saving the agent action, agent reward, and also agent state that will save in the memory size. And also we have the memory warm-up size that equal to 200, and we have the batch size, learning rate. Then learning rate itself is really useful for the neural network. And also we have the discount factor gamma that just now we talked that it will use for the future reward. And also we have the epsilon that used for the balancing between the exploration and exploitation. And we have the epsilon greedy decrement. And also here's the topology of this research proposed method, which is SETL DQN. So in here, we have the access point, which means that we put the agent at the access point, and also the access point itself receive the frames from the stations. When the station send the frames to the access point, it will result the collision probability, interference to the updated the contention window threshold value. And then, of course, the agent inside the access point will broadcast the new contention window threshold to the stations. So the access point will broadcast the new contention window threshold value itself to each station via beacon. And after that, the each station will use this contention window threshold to update its contention window value. Now we will move to the simulation setup when I just run the command of python 3 experiment.py. Now because in this research paper, the main point is we would like to compare between SETL DQN and also CCOD DQN. So in here, we see ops underscore dim, which means observation dimension that equal to 2. We have same observation dimension that equal to 2. What does that mean? So observation dimension itself, it means HPCO or history of recently observed collision probability. That's equal to previous and then the current collision rate. And then now we have the action dimension that equal to 8 for SETL DQN and then equal to 7 for CCOD DQN. So for the agent section, we have the SETL DQN that equal to 128 to 1024, which become the range of the contention window value for SETL DQN itself, and also the adjustment of the action value of integer between the 0 until 7. And also we have the CCOD DQN that equal to 16 to 1024, which is the adjustment of the action value is integer between 0 until 6. And the contention window value of the CCOD DQN itself is equal to 16 to 1024. Okay. And then now we will compare between SETL DQN, CCOD DQN, SETL algorithm, and also standard X02.11 AC. We can see here is the SETL DQN as the proposed algorithm for this research. So we can see here that we have several results, which is the contention window threshold value for SETL DQN, and also the contention window value for CCOD DQN. We have this at the station 10. We have the solved collision rate. We have the aggregate throughput. Okay. Now I would like to talk about the contention window. So we can see here at the SETL DQN and also CCOD DQN, it looks like same value, but actually it's different. For the SETL DQN, 128, it means that is the contention window threshold value. And then 128 for the CCOD DQN, it means the contention window value. So we can see here, CCOD DQN itself, the contention window value is a fixed value, no matter the packet transmission is successful or no. But in here, at the SETL DQN, we define the contention window threshold value as 128 as the threshold value, and then the contention window value, it may increase or decrease. Later, I would like to explain about in the simulation result for more detail. And then we can see here at the station 10, the collision rate of the SETL DQN, it has a bigger rather than the CCOD DQN, but it's okay. It's just have slightly bigger rather than the CCOD DQN, but SETL DQN has a better result rather than the SETL algorithm and standard X02.11 AC. But we can see here aggregate throughput, they equal to 6, the aggregate throughput, we have a better throughput rather than the CCOD DQN and also SETL, and another addition is the standard X02.11 AC. So now we will move to the contention window optimization. Oh yeah, I just want to explain that here the aggregate throughput that is different this is different with the normalized saturation throughput, because in the normalized saturation throughput, it will divide it into the channel bit rate. Okay, now we will move to the contention window optimization. So in here we can see that have the CCOD DQN, that CCOD DQN the contention window for the CCOD-DQN and the contention window threshold for SETL-DQN. So we can see here is count from 10 until 150 with the interval 20. We can see here at the light contending stations from the 10 until 50, the contention window value is moving exponentially, which means they multiply by 2. We can see at the 10 station, we have 128 for the CCOD-DQN, and for 30 station, we have 256 for 30 stations, and also we have at the 50 station, we have 512. So, but we can see here at the heavy contending stations from the 70 until 150, the contention window just turn to the maximum of contention window. You can see here from the 70 station to 150 stations, the contention window is changed to 1024 for 90 until at the heavy network loads. So it means from the introduction that I took, why selecting the contention window size is really important. We can see here that the maximum contention window at the CCOD-DQN in the heavy network load will cause the stations need a larger waiting time to send out the data packets. So it means at the CCOD-DQN, they cannot adapt with the higher contending stations. But we can see here at the SETL-DQN, as the proposed in this research proposed method, we can see here that the contention window threshold value is moving or adjusting linearly. We can see here at the 10th station, we have 128. At the 30th station, we have 256 until 1024 at the 150 stations. So in here, at the SETL-DQN means it don't need a larger waiting time to send out the packet transmission at the light and also heavy contending stations. But here, I would like to add more explanation. So so in here at the SETL-DQN, we define the threshold, and then at the CCOD-DQN, they define the contention window value. So for example, what I mean is when the station, for example, when the station is in the 10 stations, the contention window value will just has a fixed value, which is 128 in the 10 stations, no matter the transmission is successful or fail. The contention window, the contention window for CCOD-DQN, it won't change, because they think for the 10 stations, it is the appropriate value for setting the contention window. But it is different with the SETL-DQN. For the 10 stations, we have the contention window threshold, which equal to 128, which means we only define the threshold value. That means the contention window will able to still increase or decrease. And it's also applicable for all the stations, for all of the contention window versus contention window threshold value from the 10 station until 150 stations. Okay, for now, I would like to talk about the simulation result. So in here, I would like to talk about the static topology collision rate comparisons. Here, we have the collision rate comparison. We have the standard X02.11ac, SETL algorithm, CCOD-DQN, and SETL-DQN algorithm. We can see here at the collision rate, SETL-DQN have the slightly higher of the collision rate rather than the CCOD-DQN, but SETL-DQN have a better collision rate rather than the SETL and standard X02.11ac. So the question is why the SETL-DQN have a higher value rather than the higher collision rate rather than the CCOD-DQN. It has the correlation with the result for the contention window. So like I said before, that the contention window, if the contention window just move to the maximum of contention window, it will have the lower of the collision rate. But the waiting time has excessive or have a larger waiting time. But for the acetyl DQN, even it has a higher, slightly higher rather than the SCCOD DQN of the collision rate, but it has still better because it will have don't just have a smaller waiting time rather than the CCOD DQN. That one, but we can see here, here's the point. The normalized throughput is between 0 until 1. We can see here that this SETL DQN has a better performance rather than those three algorithm. That we can see here from the light until the heavy stations or heavy contending stations, SETL DQN has a better result rather than the standard X02.11 AC, SETL, CCOD, DQN. And also, we can see here that we have the dynamic topology. So in here, I would like to explain about the collision rate comparison in 900 seconds from 5 to 150 station for dynamic topology. So what does that mean? From 5 to 150 station until in the 900 second. So in here, I define, for example, from the time 0 until 30 is have 5 stations, and then from 30 it will move from 30 to 60, that add by 5, which equal to 10 stations, until it will equal to 150 stations. That's took from 870 until 900 stations. And then we can see here at the collision rate, SETL DQN has slightly higher rather than at the collision rate, especially when it has the lower contending stations. And also at the heavy contending stations, the SETL DQN also can compete. I mean, can have better rather than the CCOD DQN has almost similar. And also we can see SETL DQN can be better rather than a standard X02.11 AC and SETL. I think the pattern is same like the static topology. And also we can see here as the SETL DQN, we have the better result rather than another dose of the algorithm. And also here, so here is the interval for the normalized throughput and also the collision rate. Like here is the summary of the collision rate for the for the comparison for the collision rate comparison for dynamic topology. We can see here the pattern is same, that SETL DQN can be better rather than the SETL and standard X02.11 AC. And also CCOD DQN have better rather than those, but SETL DQN has slightly higher. But we can see here at the normalized throughput also SETL DQN can be better rather than those algorithm, those three algorithm. So here I would like to talk about the conclusion and the future works. So the contention window threshold value optimization can avoid excessive transmission delays before sending out the packet under light or heavy network loads. And then the second one is the collision rate comparison make SETL DQN can adapt quickly at the light and also heavy network loads. Even CCOD DQN has slightly better than SETL DQN. And also the normalized saturation throughput of SETL DQN shows the outperformance over the related backup algorithm. So here is the future works. So in the future works, we would like to plan to apply the SETL DQN with more realistic network condition, which is optimizing the multi-rate transmission, for example, when stationed in higher or lower transmission rate in wireless environment. So that's all from me. Thank you so much for your attentions. If there is any questions, I would like to give the best answer that I could. Thank you.
Okay, thank you for the presentation of the. So it's time for a question. Professor Ma, would you please first?
Okay. Okay, yeah, this is a very interesting topic for your research. And I have some question I want to ask. Can you change the slide to the 17?
17, okay.
Yeah. So in here, what does the data set for training come from where? Your data set from real world or you create this data set?
Oh, of course, no. This one, right? The QM parameter.
Yep.
This is from the, what is that? This one is actually come from the power and pedal. So yeah, it's come from power and pedal.
Okay.
It's already set.
Okay. So another question: how long the training time for this your approach? The training time.
Okay.
Because
The train.
you can say.
Right. Sorry. Yes. Okay. So the answer is it depends on the number of stations. For example, actually for the 10 stations, then the training and also its difference between static and dynamic, because static has a fixed number of stations, right? And then for example at 10 station, for the static station, I think it's took for 15 minutes for 5,000 seconds for that for 5,000 simulation. Yes. And then but when at the heavy network loads, for example in 150, for the static topology, it could take one night, honestly. Yeah, it could take one night because it's really have what is that contending, they will just competing for competing stations.
Yep.
It depends
So
on the network
the
load.
training time or maybe your testing time. This is your cost or 12. So I would suggesting you can add the 12 or cost to your thesis. Yeah,
okay.
This is because this is your 12. Okay. And I have some suggestion. So in your content, in your thesis, you can see in page, let me check. In page 4, they have shown some error, bookmark not defined. You can see your thesis.
Oh, page 4,
Yeah,
sorry.
page 4. Yeah. Okay. Oh, in your version, you already correct, but in my version, they have some error. Okay. And the other suggestion, the reference format should be novelty and consistent. Your reference.
My reference.
Yeah, your reference format. I can see a lot of format, so you need to let the reference more novelty and consistent.
Okay.
Yep. Okay. This is my question and suggestion. Thank you.
Thank you so much, Dr. Ma.
Okay, thank you for Professor Ma. And I have some question. The first one is about the performance in your simulation result. In figure 4.11, the normalized throughput of Stato DQN is better. However, in figure 4.10, it seems that SETLO has a higher collision rate than CCOD, right?
Yes.
So your proposed method have a higher collision rate, but also have a good performance, a better performance. Why?
Yes.
The collision rate is higher and the throughput is also higher. Why?
Sorry, I didn't get.
In figure 4.10,
Yes.
your method has a better collision rate.
Yes.
Right? No. I mean a higher collision rate.
Yes.
Much more, a higher collision rate. So your performance should not good as CCOD, but in figure 4.11, your performance is better than CCOD.
Yes.
So it seems conflict.
Okay. I'll take to explain. I'll take to explain more.
Okay, you please go back to check your data. And in figure 4.5, figure 4.5, go back to page 13.8.
This one.
Yeah, this one. I would like to know what is the average value of CW in your proposed method? Do you have the data, the average CW value?
The average for CW
Yeah,
value for
you just give me the threshold, CW threshold, but
Okay.
not the CW average CW.
Okay. So for the acetyl DQN, we didn't in here in this research paper, we didn't put, or we didn't focus for the contention window, because here we just focus for the contention window threshold, that one.
Yeah, I know. The CC in CCOD, the contention window CW value is fixed, right? But in your proposed method, it's not a fixed value.
Yes.
But I would like to know the average value.
The average value, no, we didn't define the contention window value. Because it depends on the network scenarios itself.
So in your simulation, you can collect the result, the data, right?
Yeah, because we just focus for the contention window threshold, not the contention window, because it still increase or decrease, depends on the conditions of the network itself.
Yeah, I means that could you collect the average value in your simulation? Could you derive this data in your
think no, I think because it just for the contention window threshold.
Just the threshold.
Yes, just the threshold, not the contention window.
Let me say something. We can collect the contention window. I will show you, Leah. Okay.
So I means that if you can provide this data, that is the average value of CW, your proposed method, then you can make a clear comparison. Also, in this figure, you show that in the legend, you write down CW value versus CW threshold value in static and dynamic topology.
Yes.
I think in static and dynamic can omit it.
Oh, okay.
It's confusing.
Okay. Get it.
If it is, I realized that I finally realized that you use this value both in two topology, right? So okay. Go back to page 3 in your thesis. Page 3. Some small suggestion. No, page the chapter 1 in chapter 1.
Sorry. Okay, this one.
In the first paragraph, 1, 2, 3, 4, 5. The fifth line from the bottom in the past. Yeah, you have highlight SIF seconds. Why you say seconds?
Yes, the one. I just realized just when I review my manuscript.
So you already noticed that it's not proper to say.
Yeah.
It's improper to say that,
Yeah,
right?
yeah. Mm.
And, page 6.
Okay.
Page 6. I think the page 6, you are talking about the result in your reference 20 and 21, right?
Yes.
I think that it is too long.
Oh, okay.
You can simplify some description. I think it's too much.
Okay.
And in page 8, the sentence above figure 1.2. However, a successful transmission at a heavy network load will keep the CW at the maxima. Why? I'm confusing. A successful transmission at a heavy load will keep the CW at maxima or minima.
Okay. Okay, this one has the correlation with the result for this one. This is from 70 until 150. We say that is heavy load, heavy network loads.
Yeah.
So the contention window will just choose to the maximum of the contention window, which is equal to 1024.
Or still keep at
yes.
the maximum value. I know. Okay. And in the same page, 8, the first line from the bottom, the first line, figure 1.3 is shown. I think it's not correct. It's a grammatical error. It's shown the.
Yeah, it's using verb 3.
Is shown?
Yes, shown is verb 3.
Shows. Just shows. Why is shown?
Because it has is in here. If shows, it means is just deleted. Because it could be it. The one.
Okay, that's important.
Yeah.
And figure 1.3, next page.
Okay.
It seems that the CW minima is 32, right?
Yes.
But in your simulation, I find that your parameter setting is 16. On page 35, you list your parameters. Your CW minima is 16.
Okay.
So, why is different?
The differences is all because at the SETL algorithm in the related works 30, they are using X02.11b. So it means that the X02.11b, the contention window minimum is 32. Okay, but in my
it's AC.
Yeah, it's AC, which means the contention window minimum is 16.
Okay.
Yes.
And wait for a moment. Please go back to page 2.
Here?
Yeah, in this flowchart, I think there's something wrong in the figure 1.1. I think the backoff, the meaning of backoff is to solve the collision problem. The purpose of backoff is to solve collision, avoid collision. But in CSMCA, the backoff is performed before sending data, sending the frame, not after got the acknowledgement. I think it's wrong.
Okay.
The flow is not correct.
Okay.
Moreover, in RTS, CTS enabled CSMA CA mechanism, there should be no backup.
Oh. Okay.
Because RTS, CTS supposed have solved the collision problems. So there is no need to back up to avoid the collision.
Okay.
It's clear? You clear
Yeah.
what I say?
Mm.
But I think it has nothing to do with your proposed method. But anyway, in the introduction, you should not deliver a wrong flow chart.
Okay. I'll like to fix it later.
Okay. Finally, a very small question. Go to 38, please.
This one?
The second sentence, the number of nodes has been sent from 10 station to 115 station with 20 interval. What is 20 intervals?
20 intervals means from 10 to 30. It has 20 intervals.
Oh, okay. Oh, okay. And could you please go your slides, page 18, your slides.
Oh, sorry. Slide.
Yeah, 18.
Mm.
You say that in CCOD, the CW value is from 16 to 1024.
Yes.
But it seems that there has limited value only, right? I remember you say seven value only. For example, it cannot be 17, 18. It's impossible for CCOD to have such a CW value, right?
Yes. Sorry if for 16 to 1024, it has the adjustment of the action value. It has the correlation with this one.
Yeah. So
Yeah.
only 7.
Yes, only 7.
But so only 7. How about the number? The number of state?
Number of state is 2.
2.
The number of state.
What did you call a circle in this figure? A circle.
Oh, this one just what is that? The contention window. The moving for the contention window.
Yeah, I mean, I said, may I call it a state? No.
Yes, I think yes, it can. For the first, we usually.
I don't think so.
I usually say that is initial contention window, and then this is the first contention window, the second contention window, that one. But I don't know whether it can use for state or not.
Okay, so there are 7 values for the
Yeah.
contention window.
Yes, that is this circle just want to make sure that differentiate between the initial value to until the maximum value, just that one.
So how many contention window values in your method?
Okay, my method is 21.
21.
Yes, this is actually for SETL algorithm, but because in the SETL DQN we adopt this one, and then for me for the SETL DQN, we have the 8 of the contention window threshold value.
Oh, okay. So
That one.
yeah, different. Okay.
Different.
Thank you. That's all my question.
Yes. Thank you so much, Professor, for your question.
Okay. So, how about Professor Kerr?
I just want to say something for because Professor must ask the first questions whether we what kind of data set we use. Actually, we don't use any data set. We write the simulation tool by ourselves. We implement the simulator in Python. We assume each node has always data to send, and during the transmission, we do the training. After training, maybe we have 5 or 10 seconds to get the data using the model to get a result. So we don't use any data set. I think that will be correct answer for Professor Ma's first questions. Okay? And for Leah, Professor Chen has asked you to get the average result for the SETL DQN. I will teach you later, and then if you have time, you can try to implement it and measure and put it in your thesis. Okay?
Okay.
Okay, I don't have any other questions.
Mhm.
Okay?
Okay.
So you can leave it because we need to discuss your score. Okay?
Okay. Thank you so much.
Can leave. Bye.
Bye.
Now.